Swayam Prabha. Digital India. Educated India.
Today our topic, and I would speak about some new results which we obtained, and some maybe a little bit older, but connected with our research. So this is in fact the case, but the wind is also part of these ambient conditions. So we want to harvest from the vibration. However, wind can interact with some structure, mechanical structure, and then can induce some oscillations in different way. You have very strong or weak influence to the ambient conditions, and then there are some ideas how to adjust the proper device to the wind conditions, and you know that there are some turbines, and the turbines are usually very large size. So we are thinking about small device which could be like a bluff body, and the bluff body could be placed in some on the way of airflow, and then there could be some interaction between the bluff body and the flowing air, and then you can imagine that there would be some effects like vortex creation. So vortex creation and shedding is going to excite the bluff bosy if bluff body is mounted on the flexible suspension. So this is we are thinking about some oscillator which could also work as a bluff body for the wind. So this would be such an obstacle for the wind, and one of the possibilities to have some cylindrical shape. And the cylindrical shape would be, I would tell you that it would be a good shape because we can be sensitive to some velocity. So not for all velocity it would be good device, but some range of velocity. And there is such a good thing because you know, if the wind is very strong, it could be dangerous for device. So there is some advice just to work in the limit of a slow flow, like a small velocity air flow, and then this vortex-induced vibration, so-called vortex-induced vibration, would be a good mechanism. There is also some other mechanism which is called galloping effect, and the galloping effect is sensitive to higher velocity, and we also investigate some combination of shapes because galloping effect it is the most easy to get if you have some flat area. You can imagine that flat shape, like rectangular cross section, and if you have some flat area, you can see that inclination can be changed. Inclination can be changed for the flat area, and when you have some Bernoulli law and some additional pressure is appearing. So for the wind flow would be some lift force, like for airplane. Lift force can appear, and if you have such a force, then you can imagine that there is one possibility to get the device aside the flow, and the second is the restore force from from the suspension. So it is like, for example, cantilever beam is again the suspension, and there would be some oscillation because you have two competing effects. So let me go further. So at first I would like to speak about some motivation and introduction to the vortex creation. So I started to discuss this, and then I will show you the geometry and the flow dynamics, the role of nonlinearities. It is also interesting point, and I can tell you in the beginning that if you are talking about vortex-induced vibration, then you know there is such a kind of resonance again, because vortex shedding has some specific frequency, and the frequency, so the frequency would be related to the size of a cylinder, so the diameter, and also to the wind velocity. So you can imagine that if you have ambient conditions, the velocity is changing. It's not constant. Wind velocity is not constant. So if such conditions are variable, then it is useful maybe to make broader band of good oscillation. This is the broader band of excitation. As I told you, that there is at the first point I told that there is such a vortex creation and shedding frequency, and during the shedding there is some pushing of a black body to the different direction, perpendicular to the flow. So you have a flow direction, and the body would be moved perpendicularly to the flow, because the vortex would be shed at the edge of a black body, and then you can imagine that there is some matching of a frequency, which is excitation frequency from the shedding, vortex shedding, and natural frequency of a mass spring oscillator. So the mass spring oscillator is the cantilever beam with a black body, which could be of a special shape, and the shape we design the shape in a special way. For example, we want to have vortex induced vibration. So for this case, we have such a cylindrical shape. Yeah. And it could be galloping. Galloping effect is maybe more. It could be good for us. You know, the lift force would compete with the restore force from the spring. Yeah. So when you have some oscillation, and it could be some stagnation. Yeah. You should be careful, because there could be some stagnation, but the lift force is like balanced by the spring, and there is no motion. Yeah. But it is in such way. For example, if we have too big mass, yeah, we have too big mass. So we try to reduce the mass of a black body. Yeah. So it's, to avoid such a situation, and for smaller light, you know, and the light structure, then it is working. But if we have more heavy structure, then stagnation could be present. Yeah. So then I would speak about two cylinders at the end. So if two cylinders are present, they can interact. They can interact with some kind of vortex creation. So if close each other, when the vortex could interact with one body and the other body. But you know, you can also intentionally propose some coupling, like a spring coupling or magnetic coupling. But we are also doing that. Yeah. So I would try to tell some comments on that. Yeah. And here there is a configuration. So it is possible to, you know, for such configuration, it is possible to design the experiment in the wind tunnel, and also it is possible to do calculations in, and we did some calculations in ANSYS. ANSYS, this is like a finite volume approach. So you see, for that system, you have a bluff body and the cantilever beam. Yeah, and this cantilever beam is clamped somehow here at the second end. It could be also the other way, but you have some flag. So you have a bluff body and the flag, which is moving on the as a tail. But this is also a topic which we investigate, but I'm not going to report this. So there are many configurations. So the bluff body in these configurations can move. Yeah, can move. So you have some relative movement of a flow, and also bluff body can move. And this is the cantilever, which is providing the spring effect, and also there is a piezoelectric which could be attached in the beginning of this cantilever. So now let me check. This is the. There are different regimes of the flow, and you see that the Reynolds number it's a specific number which is telling you if the flow is laminar or turbulent. Yeah. So we start from the low number, when you see that this is the laminar flow, and why we know that this is laminar flow, because you see the streams, they are not intersect, so there is no mixing in the flow. There is no mixing, but even here there is a laminar flow. You have some creation of vortex, but the vortex, they have separate streams, so there is no mixing. So vortex can be created, but you still have some laminar flow. And if you go to the higher Reynolds number, then you can see like this. You go like this, so you can see that the vortex is stronger, and the vortex is coming is created at the edge of a bluff body, but it is going with a. The shape of vortex is a little bit on the back side of this bluff body, cylindrical bluff body, and this illustration is only for stable cylinder, and in our calculation the cylinder would also move. Yeah, so this is the difference, and finally, if the Reynolds number is 2000. You can see that there is it's not possible to follow each of the lines streamline because there is a mixing of this line. So this is like a turbulent regime. Yeah, there is a turbulent regime. So we are working on the border of this turbulent and the laminar, somewhere here like 100. This is our case, because you know, the system is also, the Reynolds number is also dependent on the medium, and in our case is a medium, and if we have the same velocity for the water, then we could be still in the laminar regime, but we can go to closer to the turbulence, somewhere here, 100, and when it is still possible to make some assumption like that we are close to the laminar. So this would be some approximation in ANSYS. Yeah, but it is in fact turbulent regime. So we have a little bit mixing of different areas in our calculations. So this is some summary. The summary is that you have some kind of a transition to the turbulence is around it's above 100, and then laminarity could go together with vortex. Yeah, so the vortex could be there, and the vortex creation and shedding is fine. And it is also possible to do some energy harvesting in the water. But we haven't done such experiments, so we are working with a wind tunnel. And I will show also some video later on that. So you see that the Reynolds number is defined here, and you have also rho is like this is the density of air and density of water, but you have also some combination of these different laminarity and ingredients here. Yeah. So this is this could be the case, but water is more laminar than air. Yeah. And this is the wind tunnel. So the wind tunnel, you know, the schematic picture, the wind tunnel. So the air is coming from this side and going outside on the other way. It could be also closed wind tunnel, but we still have the air is circulating in some channel. However, here you see that there is some honeycomb which is making laminar. Or maybe not laminar, but uniform flow. Uniform flow. But uniform flow means that you have some the similar flow in some areas. Of course, you need large enough wind tunnel to draw some good conclusions because it could be fluctuating. When I was in China. I noticed, and I discussed with colleagues, we have with China such a project. I would tell you that this is like a project which we had with Sheng 2, yeah, the project which is now finished. But when I was in China, I noticed, and I discussed also with colleagues that you know, the wind tunnel was quite big, and the end was. Going through the window, yeah. But it was sometimes windy weather, and when the flow was there was some fluctuation of flow because the wind was coming from this side. So there is a fan which is drawing which is forcing to the flow from the left to the right, but sometimes you have wind from outside, you know, window, but it is coming into the that wind tunnel from the other side. Yeah, so there were some fluctuations. So we waited for good weather without such a strong wind, yeah, to make some experiments. And here you can see this is also our paper, and we discuss different shapes. I told you that there is one possible shape is that we have cylindrical shape, and the second possibility is rectangular cross-section shape. But this is like a combination of different shapes. You have a flat area in some different configuration. So you can tell that there would be some vortex-induced vibration and also some effect of galloping. Effect of galloping can be understood in such way because you see that if this maybe here it is better because there would be some flow to the backside. If you have such a area which is flat and this bluff body is going to move to forward and backward, so you can see that there would be some orientation of this wall would be on different angle. And the angle, it is important in the Bernoulli law because you can expect there would be some additional pressure. So the additional pressure and the lift force would appear if you have such additional pressure. And if you have original cylindrical shape, then the angle is not important because the wall would be always cylindrical. Even if there would be some motion, this wall would be still the same because it is like a circular shape. Circular shape for each angle, it would be the same shape for the flow, for the air flow. Yeah. So it's a mechanism of vortex shedding, and vortex shedding is not very strong for the rectangular shape. It is stronger for cylindrical shape. It is interesting point. Yeah, but the different effects are more represented for different shapes. So these are original shapes, and for these original shapes, you can see that there is some different response. So it could be like a vortex-induced response for the cylindrical shape, and the cross section is circular. Yeah. So this is this violet color. And also the galloping effect is going to be large effect, but for larger velocity. I told you that there is such interesting feature that vortex-induced vibration you can harvest energy from some interval of velocity. So this interval would change. However, if you change the diameter, and also you can change the property of a medium of this liquid which is flowing here. So when you can shift this region somehow because vortex shedding would be different, and we should be in matching area with a natural frequency. So this is a kind of resonance. So vortex shedding is it's a forcing effect, and natural frequency is the effect which is like related to the oscillatory feature of this bluff body and the beam. So it is in fact interesting to make some mixture of these two and check what is going on. And we investigated some mixtures, and you for the mixture you have some improvement with respect to the galloping effect, but so there is some increase because of the vortex shedding, but still this is like a galloping effect. It's not going down, but it is continuing because of the flat areas. You have some flat areas which are working like in the galloping regime. Yeah. So there were some some comments, but it could be useful sometimes. However, you can improve maybe lower velocity response for the galloping is for rectangular shape, yeah. And I told you that the galloping for rectangular shape is present because in the motion you can change the you can change a little bit the angle of the blow body, yeah. The blow body angle could be changed, but it is not only that this is like a twisting, but it is also that the blow body is moving. And if blow body is moving, then there is some relative velocity. So the relative velocity would have a different direction. And if you plot relative velocity with respect to the blow body, there would be some change of the angle, even if there is no twisting, because the blow body is going up and down, up and down. And when there is some kind of resulting velocity with respect to the blow body has some different angle. Yeah, I mean that. So in the case of a circular, there is for each angle the shape is the same. Yeah, so the cross section is the same. Yeah, so you can have a little bit like because if blow body is going down, then you have the velocity of the flow is a little bit up. Yeah. With respect to the blow body. So there are different effects. However, in our case, there is also some small twisting of the structure, but the beam is bent. Yeah, so there is some additional effect. However, these two are working together because we have also different configuration where the suspension is not from the not horizontal, but it is vertical, and the galloping effect can also happen. Yeah, so the galloping is coming from the variability of a direction, of a flow direction, because of a motion of a blow body itself. Yeah, so there is such a galloping effect. However, if you make a mixture of shape, then there is some earlier increase and some stabilization on the top, because this seems to go infinitely large, but of course it would be also limited because we have some spring. Yeah, the spring would stop the increase in some you know, with some amplitude, because this is like a vortex. This is voltage. Yeah, so voltage here it is plotted voltage because I told you that. We put some piezoelectric here. This is like a piezoelectric patch. This is similar patch as for the shaker. Yeah. So the system is quite similar, and I also told you that this structure is light. Yeah. So we also made some experiments with styrofoam. Because styrofoam is very light. We also had some 3D printed samples, and I will show you some examples later. So there are some results here, and for the mixture of the shapes, and there is another comment also to the first. Even this one, yeah, system, because I told you that there are some additional nonlinear effects, but here, if you look to the mechanical structure is linear. However, the interaction between flow and mechanical structure is nonlinear, and this interaction, this is vortex-induced vibration excitation is nonlinear. Yeah, excitation is nonlinear, but in such way, it is nonlinear in such way that it is providing some kind of a periodic excitation. So the vortex is shed on the left and on the right, yeah. And if it is if the frequency of the vortex shedding is the same as the natural frequency of a mechanical oscillator, then you have some repetitions of that, and it is working properly in the resonance, like here, yeah. So we have the maximum of output in voltage, but this means that this is also maximum output in the amplitude, mechanical oscillator amplitude. So this is there is such a possibility to put some splitters. The splitters are placed for to form a different flow, you know, to organize flow in different way. So you start from the cylindrical shape, but you put some additional splitters. So the splitters would form some different kind of circulation of air, and this is also interesting. But these shapes has also something like that, and the splitters are also flat areas. So you can imagine that this is also a similar kind of effect, but this is like a mixture of the flat areas and the circular, and this could have some good response. And we studied different angles, yeah, different angles in different configurations with different angles of the splitters. Yeah. So the splitters is one of the interesting topic which could be done here. And I told you that the interaction between wind and oscillator is nonlinear. However, oscillator itself is linear. And later we also studied some you know, some other cases, but we can have also nonlinear potential, because here it is potential only spring potential from the beam, which is for some range of deflection it is linear. Yeah, but we can put some magnets or something like that, or springs, so additional springs which could create some geometric nonlinearity, and this could be nonlinear. Yeah. So here you have some, I told you that sometimes we are working with a styrofoam, and the styrofoam, we wanted to make some channels inside the black body, but in a styrofoam it was difficult to make a channel. So this is in fact not our paper, but this is the paper by the Chinese group, and they studied some reorganization of the flow by some special channels which made on the surface of the black body. Yeah, so there are some inlet and outlets on the black body. Yeah, so you can study such change of the flow. Yeah, so the flow is even more complicated. However, you can see that this effect is a local effect on some because it was difficult to make the channel in the whole black body. Yeah, so for some test it was only limited to some small range, yeah, of a length. The channel was created, and this was studied by the Junlei Wang group in Chongzhou University in China, and they discovered that creation of such making such a channel it is by creation of these channels, it is possible to make stronger vortices. Yeah, so with like a very strong vortex can be created in some configurations. So when and this is in fact interesting effect, because if the vortex is stronger, when we have stronger forcing. Yeah. So I told you that the vortex creation and shedding is a mechanism to force the black body. Yeah. So this was done by Chinese group, and you see that there were many results, but I want to summarize just few of them. And this is the voltage output, and this is the displacement output. So you can see that it is in fact not always positive to make such channels, and you should design channels in a special way. And if you have this is S is called S, but maybe I can this is S. Maybe S is like a single channel. It's a single channel. In this definition, S means it's is single channel, and the double channel is D, and the A is like an asymmetric channel. Asymmetric double channel is E, because you have it is related to the number of inputs and outputs. So if you have S is like a single channel, and the angle is 60 degrees. Yeah. So if I go to this, and this is called this is called single channel. Yeah, single channel. But single channel, but the input is in front of a black body, and the output is going with some angle, and the angle is like a 30, 60, and 90, and the baseline is without additional channel. So you see that, for example, 90 degrees is not very good, and 30 is not good, but 60 is taking you larger interval of wind velocity, which could be variable. Yeah, if you have some variable wind velocity, it is good to have such a larger interval. So this is the aim of the study, that how to increase this interval. So there could be some kind of a channel. You can create such a channel to increase. Yeah. And we started also by doing some experiments. We had such a sample which we prepared by 3D printer, but this is and this was done together with Dr. Ravi, who spent in Lublin some time and still still he has a job in Lublin, but he's now visiting Vellore. Yeah. So thank you. So I think that this is only a limited study to some two-dimensional flow, because you can from the previous configuration, experimental configuration, you can see that it would be better if we have three-dimensional calculations, because the channel is located not for the, it is not extended to the whole sample, to the whole cylinder, but in some only in some area. It is working in some area, and this is the cross section exactly at this channel, in the level of a channel, and you can see that this is there is some limited application of such calculations, but we wanted to see the tendency. The tendency, what is the tendency if you have some different channels and you perform calculations? And I would tell that the similar argument was in the Wang paper. In the Wang paper, you see that this is also not the hole is not in the whole cylinder, but it is located, and they did this estimation. I must tell that they did mostly experiments, but maybe there is some calculation, if I remember. Well, there could be some calculation with one for the two-dimensional system. Yeah, but usually this group in China, in Chongzhou University, is very good in experiments. So I mean that our configuration was studied with a similar approach as the previous paper, and then we have done some ANSYS analysis. So you see this turbulent, with like a turbulent kinetic energy equation, because we are working in turbulent regime, and then dissipation rate equation. Yeah, so we have number of equations, and we used ANSYS for study, and here there are some pictures of results similar to. Plotted in the similar way as in Wang, this Wang paper, and we had this is like a symmetric channels. Yeah, so these are symmetric channels. So in Wang paper they studied symmetric and asymmetric channels, and also single channels. Yeah, and but here you have some example of symmetric channels, and in the symmetric channels it is possible to notice that if you have 60, with like a 60 degrees channel, so the inlet and outlet, so it is the vortex is stronger. Yeah, so you can just tell that this is like a stronger vortex. You can see visually that it could be stronger, and we have some more results, but I presented just few of them. So this is actually different velocity. So we're starting from 2, 3, 4, and you have 30 degrees and 60 degrees. Yeah. So and here there is some increasing like a 5, 6. So most of time this vortex is stronger for the 60, which is consistent with the Wang results. And here there is some simulation, but I'm not sure if it would work. Yeah, there is some visualization of this calculation. You can see that it is moving like that. Yeah, and it's the initial condition is that it is not moving, but then if you start a flow, it is going to move. Yeah. Or maybe you don't start the flow, but you just in physically there is a meaning that you keep this not stable, but you release, and then it is going to go up and down, and this is the we in our system we had two-dimensional calculations. However, we estimated the force for the whole cylinder, and then there was an assumption that the holes are along the cylinder. Yeah, so this is like a wrong assumption, but we wanted to see the tendency, because otherwise it is not possible to apply two-dimensional flow simulations. Yeah. So this is from you see that this is going to be periodic motion, and of course the flow is from this side, so you see that if there is also black body moving, the angle this direction of the flow is different with respect to the black body. Yeah. So, but it is cylindrical shape is the same, still the same. However, the channels are not the same. Yeah, because sometimes you can think that. If it is going down, then you can this outlet channel can also work like inlet. So this could be a difference in the flow direction inside the channel. Yeah. This is that one, and we did also some experiments with our. We did also experiments with some 3D printed samples where we had the channels inside. Yeah, so we have even 2 channels. Yeah, but the flow would be like that. Yeah, and it could be mounted in such way that this is exactly the inlet, but the inlet could be with angle also. So we tested different configurations, but I will not show you all the results. But this is one of the results, and you can see that this is in the wind tunnel. This is in the wind tunnel. So we can observe such a motion with a sample. The inlet is with angle, and the outlet is exactly like a backside. Yeah. So we changed also the angle, but it was possible to see that there is a good, it's a good, relatively good amplitude, and you can see also there is because this is the wind tunnel. You can see the also the you can see also the velocity. Velocity is somewhere here. Velocity is 2 meters per second. Yeah, so it's like wind velocity is 2 meters per second. Yeah, I will give you this presentation later. Yeah, so I mean that this is the interesting, and there is another sample which has very similar mass as the previous one, but there is no hole inside. Yeah, and it was worse performance. Yeah, so we have a little bit different velocity because it was recorded for some different velocity, but we checked some other velocities as well. So you can see that in this kind of there is only such a small effect, and also twisting, a little bit twisting, some twisting effect also. And the wind, if you look to the velocity, velocity is 6 meters per second. Yeah, 6 meters per second. Yeah, so this is this is our wind tunnel where we make some experiments, and these are not used for this experiment, but we are thinking that if there is such a large amplitude, maybe there could be some interaction. So this configuration could be also good to test what is the influence of this additional structure. The structure was intentionally prepared just to make some stoppers. Yeah, but we are not using these stoppers for this experiment. However, there could be some interaction with a vortex because they can give also some vortices to the system. Yeah, so it could be the influence of this could be still here. Yeah, but it's negligible probably. Yeah, so this is that one, and this is from calculations. So from calculations we obtained, and this was with Dinesh Kumar Ravi. So we did some summary of these calculations and published in this journal, and you can see that what is the performance with different with different configuration of channels. Yeah. So it is 60 is very good. Yeah, 60 is very good. However, some other angles are maybe not so good, because you have a base performance which is you know, in the middle, the black curve. The black curve is like a base without holes. So I told you that there is also experiment with some magnets. So you can put the magnet, and maybe you can make a vertical configuration. So if the previous situation was the configuration, horizontal configuration of a beam, but you can make a configuration vertical. And I told you that there is some twisting effect, and the twisting effect could be produced by the effect of a beam, that beam and the mass, that there is some twisting mode, but also there could be some if a black body is relatively long, you could have vortex shedding in a different time from the top and from the bottom, and then you could imagine that it would twist. So there is some distribution of vortex. If you have a relatively short black body, it could be vortex could be shed only in one way. But if you have longer, and also I heard such a presentation which was given by Professor Alam. He is working in China, but he originally from Bangladesh. So he told about such a system, that you have some fluctuation of a diameter along the black body. It is like a long black body with some special, you know, modulation, and this modulation is forcing some difference in vortex shedding in different levels. Yeah, so he told that this concept was biologically motivated. That there are some animals and these animals can have they have some sensors in the hair. Yeah, so especially the sensors can detect some kind of velocities and some perturbances in the water, and they have variable diameter, and this is very robust sensing. Yeah. So if you have a flow, then you can sense some kind of effects in the environment. Yeah, but he went further, and he investigated some periodic modulation of a black body. We haven't done for the time being such modulations, but they are doing. Yeah, so it would be interesting also to implement some other modulated variability of this black body. So we did some other some other combinations. For example, we did such a change, but you have a hybrid shape, which is on the top could be like a square, and on the bottom is like a circle. But we haven't done modulations, some periodic modulations like they did. Yeah. So this could be interesting. And here you have experiment which was done in China in fact, and this is the wind tunnel in China. I told you that this is like a big wind tunnel, but the output is going just through the window. Yeah. So if there is a wind weather, you cannot measure precisely. But the flow is going this way, and you have some sample which is like that. Yeah, so you have different phases. There is a magnet on the bottom and some magnets on the frame. So you can have some additional interaction, and these are nonlinear effects. And why we are doing nonlinear effects? It is more or less because we want to. I told you about this. Matching of the frequencies. So there is a frequency, natural frequency is matching with a shedding, vortex shedding frequency. But here you can see different solutions because you have nonlinear potential for the motion of a black body, and you can have different solutions. For different solutions, there would be different frequency of vortex shedding. So it could match. Yeah. So this is if you have different solutions, then this is also switching between potential wells, for example, and you have different natural frequency, because natural frequency is after linearization, for example. So you have, or characteristic frequency is different, and this different frequency could be obtained for different velocity. So I told you that shedding frequency could be is dependent on flow velocity, but also is dependent on the geometry. So it's like a diameter. The diameter is constant here, and this is styrofoam. It's a styrofoam sample. Yeah, so styrofoam, very light sample here. But the magnet has some mass comparable maybe to the styrofoam. So this is interesting point. Yeah, and here there were some yeah. Yeah, the size of the body. Diameter is if diameter is larger, then I think I have some study on that in one paper, but I think we can shift the interval to the larger velocities. Yeah, so we can for some larger diameter we shift to larger velocities. So for smaller we go to a smaller range of velocity, and I gave you also so I would give you such a code which we can test on the computer session. So this is like a MATLAB code, as there is some possibility to derive, a simplified model, and the simplified model is working in such way that there is a van der Pol mechanism. So this van der Pol mechanism was tested, but it can reflect the dynamics of a vortex shedding. So instead of an external sinus, you have some flow in the system, and the interaction with interaction of a flow with a black body and the forcing black body is through this additional oscillator, which is self-excited oscillator. It is van der Pol. Yeah, so the van der Pol system, and there is some limit cycle solution in the proper words, telling with proper words, and this kind of periodic behavior of the oscillator is forcing the mechanical structure. Yeah, so this is the mechanism. I'm not sure if I presented. Maybe I presented here. Yeah. So this is the additional you know, oscillator, which is using some Q variable, and the variable is it is like a fictitious variable, but it was checked that it is well there is a good reflection of a vortex shedding mechanism. So you need to use some parameters which are just found in the experiment, and you have coupling. You have coupling to that Q should be coupled to the mechanical system. Let me check by this force A. Yeah, you see that there is a Q here, and also X dot, which X dot is like you know, it's a mechanical structure fluid interaction. It's a usual mechanical fluid interaction, but this one effect is coming from the Q. It's like a vortex shedding. Vortex shedding, you solve this. This is like a mechanical structure equation, vortex shedding, and the last is the same as previous. Is like a piezoelectric. Yeah, so we have more equations, but it's possible to analyze, and I have prepared such a code for you to check. But you change the diameter and you obtain different response. Yeah. And when we tested in experiment, we tested similar. You know, distribution of some distribution of magnets, and we checked what is the distribution, and it was such a potential. Yeah, so the potential can be you know, can be modeled also by, but you need some kind of finite elements or finite volume. So this is finite elements usually, but there is like a field of it's a magnetic field which is interacting to the magnets. So the magnets are interacting through the magnetic field, and you need to recalculate the distribution of the magnetic field, and it is for different positions. Yeah, and it is possible to do this such simulations, but it is also possible to look what is the force, what is the restore force for different position of a black body without wind. So you can statically check what is the force, and this is the result. We fit such a potential, and the force is given here. Yeah. So this was one of the configuration which we studied experimentally in China, and we provided the numerical simulation by this model. This is like a model which I told you, but this is the van der Waals included simplified model. Yeah, and the experiment it's a well fit. But however, we have to use some information from the experiment, like this lambda and this omega shedding should be measured in the experiment and fit to the model, and then we can observe some good matching of these results. Yeah. But this was published with, I think, by Chinese. Yeah, I'm not sure if maybe this is published by Chinese. Yeah, but there was it is only the group Chinese. Yeah, so we had some papers in cooperation, but this is not that one. Yeah, this is the. But in some other paper, and maybe this is like a cooperation paper, because I remember these figures. Yeah, so I think for different, if we are doing some simulations, then we can manipulate with a potential, and this is simplified model. So you can check what is the result for different cases, for different cases, and you see that there is some probably some bifurcation on the way. So the switching between solutions giving different level of response in terms of voltage output. Here there is some assumption, but we have zero initial conditions. Zero initial conditions, and you see that this is like there is some notation, but it's like a tristable with T, and also bistable like B. So the bistable is different shape, because tristable is if you have three potential wells. So this is 1, 2, 3, 2 barriers. But the bistable case is that you have only two potential wells. So bistable and tristable are similar. However, tristable is a little bit better for sometimes, and it is because usually if you have more potential wells, you have the barrier is lower. so because of this lower barrier, you can have better performance in some regions. So it is easier to get a very big amplitude. It's like the largest amplitude of a response, because you see that on the way of this black curve, it's like a relatively large barrier. But if you have a red one, there is a smaller barrier. However, this is maybe on the other side, there is another barrier for the negative, the negative displacement. However, if you even compare this red one to the black one, it is lower. So relatively low potential barriers if you have multi-stable. You have more multi-stable potential wells when you have lower barriers. And this is, I'm not sure, maybe it is a video. We can check. This is the video. This is the video in China with a sweeping of a velocity. so we increase velocities, and we have nonlinear system. We have nonlinear system, and we like a short video. It's you can see how it is working. Okay. So this was our group in China, and and Professor Shengxi is here in the middle with me, So we did such a work, and this is already published. This was submitted, but it is already published, And then we have. This is published in exactly here, So we to characterize the motion, we use some method which is called 0-1 test, because we wanted to show that we have also chaotic solution. So not only periodic or multi-period periodic response, but chaotic solution. So this is one method for characterization of a solution, and it is working like for stochastic systems, but you need to check what would be the gain, and this is the the gain is like a displacement. However, displacement is difficult to analyze in such system because you have some limitation, the displacement. And in the stochastic system, for example, for the gambling, you can win or lose, and if you win or lose in a long time, it is or any time, it is proportional. Your gain or lose is proportional to the square root of the time. Yeah. So if there is such a scaling, we can tell that we have stochastic dynamics, and when we are testing what is the behavior of this chaotic system, but we had to change the variables from our x to p and q just to have unlimited system. But like for gambling, you have no limitation. You can gain and lose, but you can the increase could be is not limited. Yeah. So usually the limitation is given in our mechanical system because we have some suspension, and there is like a finite length, and we cannot go beyond this. Yeah. So there is some transformation, and after transformation to the new variables, you can use stochastic approach and check if it is if you have unlimited lose and gain, or you have some limitation. So there would be some scaling of the increase. 0 is for regular and 1 for chaotic dynamics. So there was some, for example, in time domain, there was some voltage plot like that. So you see that this is the total range to the 100 seconds, and when you have only 10 seconds, many of switching, yeah, because you have such a nonlinear potential by magnets, induced by magnets, and the flow is like 2.6, and this is the in terms of meters per second, yeah, meters per second. And here you have also this is the chaotic system. So you see that this is like a Fourier transform is like a band. Fourier transform is a band. So you can tell that this is the, it seems to be chaotic, and you have also some kind of unclear motion, which could be also some not necessarily chaotic, but it could be like quasi-periodic. But when the frequency distribution is telling you that this is rather chaotic than quasi-periodic, and the Lyapunov exponent was a larger value. Yeah, so this is like a positive. So you have of course more Lyapunov exponents. Because these are calculated by the Jacobian approach. So Jacobian is created from the variables which are used for simulations, because this is from simulations. And when you have two variables for x and x dot, and this is the phase, space. So you have two variables for x and two variables for q and one for voltage. So this is 5. You have 5 Lyapunov exponents, but one is positive. So you can tell that this is chaotic motion, but the positive exponent is not very large. Yeah. So it is it's a kind of weak chaos. Yeah. Yeah.
What is the Lyapunov exponent?
The C, yeah, Lyapunov exponent. Yeah, so I'm telling you that this is Lyapunov exponent. Lyapunov exponent is an exponential ratio of if you look for the divergence of the neighbor trajectories, it is defined like the divergence in the exponent. So it is multiplied by time, the exponent, and if exponent is positive, then you have divergence, and if it is negative, you have convergence. Yeah, but you know, usually there are different approaches to Lyapunov exponent because in general you can just calculate many trajectories which are close to each other, but the problem is that you can also look for some gradients, and this is done in terms of a Jacobian matrix. Yeah, Jacobian matrix is written for the 5 variables, and from the Jacobian matrix you can analyze some products of Jacobian matrix, and if you diagonalize this, you can get the Lyapunov exponents from that. Yeah. So this is on the way of calculations. You update the Jacobian matrix, and then you can extract some information about the divergences of the solutions. Yeah. So these gradients are telling you if you have such a divergence or not. Yeah. Yeah, and here we estimated some. This is the last curve is the distance. Yeah, so the distance is growing, and if it is a good it's a good feature. Yeah, because I mean that the k is like a parameter which is close to 0 or close to 1. But m, I will check with MC. MC is like it is the distance. The distance is growing, but this is like a square. It's like a square. This is square of the distance is growing, and the distance, I told you, this is like a stochastic, and you in the P and Q variables you have some random walk, and this is like stochastic behavior, as in gambling, for example, that you can have some gain or loss, but you can tell that this is the square is scaled linearly with the time, and n is like sampling n, so you can tell that this is linearly scaled with n, and when it is for different parameter c, you have value 1, because this is 0.96 is also close to 1. It's not 0 on the vertical axis. We don't have 0 here. Yeah. It's mostly 1, yeah. So 1 is telling you that this is chaotic motion. Yeah. So this is some test for chaotic motion, and this is periodic behavior like this. You have some range of 90 to 100 seconds. So this is the short range, and you can magnify that picture, and you see that this seems to be periodic. But if you calculate the phase portrait, the phase portrait was maybe in this MATLAB approach, we provided you some code for phase portrait. And when you calculate the Fourier transform, its Fourier transform has two frequencies, and one frequency is probably the basic shading frequency, but the system which is responding like that, it is not it is voltage, so voltage could be related to the displacement. However, you see that this is not this displacement is not circular, and when the second frequency is related to the modulation of the shape. So the modulation of the shape is the second frequency here. Yeah. Yeah, so this is the And if you look for the Lyapunov exponents, it is 0. 0 seems to be 0. The largest Lyapunov exponent is 0. And in previous chaotic system was above 0. Here it is 0, and 0 is usually obtained for the van der Pol system because we have self-excitation mechanism. There is no periodic force, so the periodicity is obtained through the dynamics. So this is like dynamical, effect of this flow and vortex shedding. Flow and vortex shedding is like a dynamical effect, and this is like you tell that this is quasi-periodic. Quasi-periodic, or there is such a it is difficult to tell about that this is exactly quasi-periodic, but because we don't have a leading frequency, which is external excitation, so we can still tell that this is like a quasi-periodic because this effect is. It could be this is self-excited system, yeah, and this is like a limit cycle. It can be also told that this is like a limit cycle solution. Limit cycle solution is only for nonlinear systems. I told you that nonlinear systems can change frequency, but they can also have such a result that there is no external periodic excitation, but the response is periodic. Yeah. So this is the property of a nonlinear system, which is not. So there are several properties of nonlinear systems, and for example, the interesting point is that the property is also given here, but this frequency is probably 3 times larger. So this is like a superharmonic. So if you have some superharmonic, then this is modulation. Usually, some modulation of a phase portrait, and also of a time series. So you can tell that. There could be subharmonic, and these two effects are related to the system. If you model the system, you have some x to the power, and if you have a harmonic solution, you have a sinus omega t. But if you take the power of sinus omega t, you can get some sinus of 2 omega t or 3 omega t, and so on, and also partial, like numbers like half omega, 1/3 of omega, and so on. You can get by taking power of a sinus. You get some different frequencies, and this is coming from the trigonometrical identities. So this is some of a nonlinear effect. I'm telling because maybe if you have this exam tomorrow, there could be like a question about nonlinear effects. so you can describe there are some different nonlinear effects. Yeah. So I mean, and also some phenomena which can lead to nonlinear effects, like impacts and the mechanical, like a friction could lead to this. But friction is also used by in energy harvesting, because we have some. This is like a tribological effects in energy harvesting, but we are not discussing this. Yeah. So this is also used in energy harvesting, but these are used especially to some microsystems, yeah, with a electrostatic design. Yeah. So this is the zero is here, yeah, and you see that this is not a very large random walk; it is going around circle, yeah. So the displacement is not growing, but it is oscillating. So I think it's difficult to provide any rule on that. And then it's like a tree-stable, because this was originally was a bistable, yeah, and I think it's like a bistable here, yeah. But I haven't written this, but this was bistable because you have some two equilibria here. You can see the two equilibria, and also this is also characteristic for bistable. But you can have the tree-stable, and the tree-stable is like you can have a large amplitude, but with some modulation like that. Yeah. So it is, and this is also a kind of limit cycle solution, the periodic solution of a nonlinear system with no external periodic excitation. So such solutions is a specific solution for the nonlinear system, and then you have also the solution which is chaotic solution. Chaotic solution could be also interpreted that this is some competing of different solutions, because you can see that if you change the parameters like velocity flow, maybe you can just close the portrait inside one potential well, and if you have some competing, but sometimes it is switching, sometimes not, and you can have multiple frequency response, or you could have some chaotic response. This is still some zero. The parameter is zero, so the zero one test is giving you zero. So this is like the result is, but this is a regular solution, and this one is also regular. Yeah, so this is regular. But on a single frequency, this is very close to the circular, and this is like an ellipse, but this is related to the scaling. If you put a slightly different scale on the maybe on the x, you can you put some different ranges. You can approach to the circular, because this is like a small amplitude solution, and you have only one frequency, no modulation, and here you can check that this is like a zero. Zero is like a regular in the 0-1 test, and this one is chaotic for the tree-stable, and I told you, but there is some competing. When sometimes it's going only in one potential well, but sometimes it's changing the potential well, going through the potential barrier, and this is also related to some accumulation of energy. If it is just if energy is enough, then it can switch. Yeah, but it is moving on the other side. You see that this is like a broad, so it is the case, but the energy is accumulated. It is a little bit larger velocity in each cycle, and then it is switching, and then the story is repeated again. Yeah, so there would be some short events with staying in one potential well and switching to another. Yeah, so multiple solutions are competing each other, just to instead of traditional superposition rule, which is for linear systems. Yeah. So this is the case, and we also did together with colleagues from Velour. Yeah, we also did some work on the interaction between different cylinders. So this was a paper by also Srija Sadasivan from Velour, and and there was Mohammed. No, it's not Mohammed. It's like Moht, maybe Moht Furkan. Furkan, and he was originally in Delhi, but he moved recently to Tamil Nadu. Yeah, but I'm not sure where it is, the location. Yeah. Moht Furkan. Yeah, so he visited also us in Lublin. Yeah, so Srija was for 6 months in Poland. And Moht Furkan, I visited him in 2 years ago. I visited Moht Furkan in Delhi, IIT Delhi. Yeah, so but quite recently, few months ago, he moved to Tamil Nadu, to some other IIT, I think. So there is a number of such universities in Tamil Nadu. And here we also observed, this is interesting, but there are 2 cylinders, and we wanted to check what is the performance, of these cylinders, and this is in terms of displacement. Yeah, so the displacement, and this is the distance between cylinders is given by the diameter. So the diameter is like S is a distance, but it could be like if you have 2.5 diameter, then you have only half diameter as a gap. Yeah, and if this is like a 3.5 diameter, then you have 1.5. Oh, this is 1.5 diameter. Oh, this is no. If you have this is like a 1 diameter is just for the radius, for 2 radiuses. Yeah, so this is this one is you have 1.5 diameter gap between the edges. Yeah, and here you have 2.5, and we wanted to check what is the response. There is some problem with this figure here. But I think maybe I used the wrong figure. Sorry for that. Yeah, but there is some problem with this line. Yeah, it's the extra line. Yeah, but anyway, it was interesting, and you see that for different diameters, for different gaps, we used. For example, for 2.5 spacing, we have estimated what is the vortex shape, and the vortex shape is sometimes synchronized, like here. There is a synchronization. The vortex is shed in the same direction, but sometimes if you go to the 2 meters per second, the different velocity, there is the different they shed vortex in different way. Yeah, so this is maybe anti-synchronized. Yeah, so this is the and if you have very large velocity, maybe this vortex is just separated. Yeah. Even for this 2.5 diameter, but the large velocity, yeah. So the vortex is set in different way, and the interaction between these 2 different black bodies are only through the vortex, because it is there is no other coupling. It could be coupling, and I will show in a minute. But we also studied some coupled system. Yeah, so there is some additional feature which is coming also here. Yeah, yeah. So I'm not sure why it is. This is just removed. Yeah, maybe now it is. Yeah.
It's like controlled by.
Maybe. Okay. Yeah, but it is. It seems to be now. It seems to be okay. I see no other feature, but it's if you go, this is the what is the difference here? Yeah, this is variation in response. Yeah, I just want to check. This is the two black bodies, and this is the wind velocity. Maybe it is the same picture. Yeah. It is the same picture maybe. Yeah. But it is intentionally plotted once again just to show you different frequencies. Yeah. So sometimes you have additional higher with superharmonics. Yeah, superharmonics, and with superharmonics are coming with a flow interaction. Yeah. So this is possible that there is an interaction between the second black body. And the interesting point was that this black body has the same radius, and we are studying also the next in the next step different radiuses. Yeah, because these are just equal cylinders. Yeah, and here there is some configuration with a magnet. Yeah, so the magnetic coupling. So magnetic coupling was also studied, but it was mostly studied in. There was some numerical, model, but we still, yeah, it is not so bad. The numerical model is not bad. Yeah, but the model was maybe simplified too much. However, we can have some sweep. In the sweep, you cannot control so easily the switching because you can have small changes, and the switching would happen with different speed. Yeah, because these two solutions could be just coexisting. So different coexisting solutions are coming. It could be, this switching in the sweep could be also related with the time of sweeping. You have a faster sweeping or slower sweeping, and then you could have different switching. So we have relatively good matching of experimental and numerical results. However, here, if you look carefully, there are some small differences, and the experimental results are more. There are some fluctuations, fluctuations in the experiments. Like usual, there are some experimental errors and some other couplings which are not included to the simulations, because simulated system is isolated very well. Yeah. So this is like our joint paper, and for this paper we had also a video. There is a video. You can see the video for this joint paper with the Chinese. Yeah. And this is a sweep. This is sweep. Xiaoxin Ma is one of the first author of this paper. It's like reflected here. And you see that these are two piezoelectrics on both systems, and they interact like that. Yeah, this is this is very interesting point. Yeah. And there is some region of very fast motion, and these black bodies are stereoforms. Yeah, stereoforms with additional magnets. Yeah, yeah. There is a magnet. Yeah. Okay. You can see in the beginning. There is another. It's another system here. Yeah. So this is now ongoing experiment in our laboratory. With tandem. This was called you know, this is not tandem. It's a kind side by side. Yeah. I'm not sure. Maybe this is. I can look. I cannot see what is the configuration here. Yeah, but it is difficult to tell. But maybe on the schematics. Yeah. The schematics was maybe it is also tandem. Yeah, this seems to be tandem as well, because the flow is in this direction, and they are just moving in such way. Yeah, and then you see that this is that one is moving now. So that one is interesting. Because we did some experiments. We are now doing these experiments, but you know, this is smaller black body and this is larger black body. If you exchange the position, then there would be not such a strong effect, because the first black body is like a waking vortex is coming to the second black body. The second black body is excited not only by flow, but also that flow is already fluctuating. However, if you exchange these two black bodies, you can get the flow and the vortex would be there, but this smaller black body would be in the shadow of the first black body, and there would be no such a nice effect. Yeah. Yeah. The magnet, yeah, because it is this is repulsive magnet. Yeah, so the repulsive magnet is moving one way, so the other should go the other way. Yeah, so this is like improving, but it is not exactly applied. So here we have different radiuses, and this is the flow with similar sizes. Yeah, similar sizes. Yeah, in both cases we have stereoforms. Yeah, so this one is. Yeah. Yeah. So I have some conclusions. So in conclusions, I would tell that I reported some new calculations on these channels, channels in the black body. So we put some channels to the black body just to change the circulation of air. And the problem was it was working quite well, especially for 60 degrees. However, the model was very simplified because we applied some two-dimensional calculations, and for the channels we had some assumption that the channel was for the whole body, but it was located in some place. But we wanted to see some tendencies, so in the calculations, and there was some previous report of Junlei Wang that this configuration with the channels is providing stronger vortices, for some angles. And if you have input and output of a channel with the angle 60 degrees, in his opinion was a good choice. Yeah. So we also studied some different angles, and 60 was again good for in our system. And we did also some preliminary experiments with the channels. I showed you one experiment, and especially it was interesting that we had such a black body which was 3D printed, and this was too heavy, a little bit too heavy to get a good response on the wind. However, if you put some channels, you change the circulation of air, and it was able to excite for the large amplitude. So when I wanted to tell that we went to the nonlinear dynamics, and when the linear approach at first was was especially related to the mechanical system. So the mechanical system is the mass and the spring. So we are telling that this is like a linear system because we need a very large excitation to get nonlinear effects. However, we avoid such extreme conditions. So the nonlinear is always the flow and structure interaction. And when this nonlinear interaction is giving us some mechanism which is like a limit cycle, which is forcing the blob body. So individual blob body is forced by such flow mechanical structure interaction, which could be nonlinear, but which is nonlinear. But you know, this is a limit cycle solution, and it is providing some periodic excitation to the blob body. So I mean that if you have such interaction, it is interesting to tell that in mechanical systems there is such a solution like limit cycle, that you have no external periodic forcing, but the periodic is response. So this is periodic response from some interaction between the elastic structure, mechanical structure, and flow. Elastic mechanical structure and flow. And if you put some additional nonlinearities, like you know, magnets, so you modify the potential, then you can get some additional solutions, and these additional solutions are important because in the original case you have for the cylindrical shape you have a mechanism which is called vortex-induced vibration. And this vortex-induced vibration is a kind of resonance, but your shedding frequency, vortex shedding frequency, is matching with the natural frequency of a mass and spring oscillator. And if you have nonlinear potential, then you have several solutions which have different characteristic frequencies. So you can broaden the range of velocity, because for each velocity you have also different shedding frequency, but you can tell that also different characteristic frequency is possible for different solutions. If you have switching between solutions, you can extend the region of interest and for sensitivity. So your device could be sensitive to the larger range of wind velocity. Yeah. So I think that this is the end of my presentation. Yeah. So thank you.